Good morning, honor students. I wanted to take this opportunity to make a video recording due to the technical difficulties we were experiencing in yesterday's session. I apologize for those, and hopefully this video will make up for what we should have heard yesterday. So I'm going to get started right now. I made a little bit of an agenda that we're going to go through today. Remember, topic 2 is pretty hefty as far as the topics that are covered. And so I just wanted to gloss over the main points that will help you in your assignments. As always, if you have questions, please email me and I can help you on a case-by-case basis. So the first thing that's really talked about in the kinematics topic is what vectors are, okay? So when we talk about vector quantities, the definition that I wrote up here for you says any quantity of measurement that has magnitude and direction associated with it. Okay, now magnitude is a fancy word for size. Direction, keep in mind direction could be negative. So I want you to go through this list of possible quantities that could be vectors and tell me whether or not they have these two components associated with them. So for example, temperature. Does temperature have magnitude associated with it? Well, yeah, we measure temperature with actual numbers, so that's got magnitude. We can measure how big a temperature increases by its size. Does temperature have direction associated with it? Well, yeah, because temperatures can be positive, they can also be negative. Okay, so yes, temperature is a vector for those reasons. Okay, so I'd say yes for temperature. Okay, next, speed. So if you think about driving in a car, does the speed that you read on the speedometer have magnitude? Yes, it does, because there's numbers associated with it. Does speed on the speedometer have direction? Not really, because it can't be negative, okay? Your speedometer is only marked in positive numbers, so speed, you would say no, because it doesn't have that direction component. Decibels, for a similar reason to speed, are not vectors because you can't have negative decibels. Distances, so if I measure the distance from here to the wall behind me, that's probably a distance of maybe 8 feet, okay? So size is definitely there, magnitude is there, but direction is not really there because direct distances are always measured with positive quantities. So I wouldn't say that the wall is negative 8 feet from me. That doesn't make sense. Okay, so distance does not have direction, so we'd say no. Okay, that's kind of a little bit about vector quantities. Oh, by the way, if quantities do not have direction associated with them, or in other words, if something cannot be called a vector quantity because it lacks either magnitude or direction, we would call it a scalar quantity. So scalar quantity is what each of these no options would be called. So this is a vector quantity. Okay, going on. So on this note of vectors versus scalars, we just said that distance is a scalar measurement. Okay, now in physics you're going to learn about a word called displacement, which is kind of like distance. So I want to talk about the difference between distance and displacement with a little bit of an object lesson, okay? So suppose for a second that I am standing here at point A. Suppose that from this point, I walk 10 feet let's say I'm going out to my car. So I walk 10 feet from where I started. I realize that I forgot my keys, so I have to walk back to point A, which was also a distance of 10 feet. Okay? So when you talk about the distance that I traveled in that little silly story, what I've written here in the first bullet point, distance takes the entire path of travel into consideration. So in this example, the distance I traveled was 10 feet to some point, but then I turned around and traveled 10 feet back. So my total distance in this example is 20 feet. okay? And that's because distance takes the entire path into consideration. When we talk about displacement, displacement is a vector quantity, okay? So it does have that direction component. It can be negative, okay? And displacement only takes the starting and final positions into account, okay? So I started at point A in this example. Even though I walked 10 feet forward and 10 feet back to where I started, I'm in the same place at the end of the story that I was at the beginning. So my displacement is equal to the positive 10 feet that I walked out minus the 10 feet that I walked back, because remember, displacement can be negative if you're going backwards. So my total displacement would be 0 feet, okay? So these little sub-bullet points, just remember that displacement is equal to x sub f minus x sub I, okay? We usually measure displacement and represent it as a variable x. So x sub f stands for final displacement. X sub I stands for initial displacement. Sorry, x sub f stands for final position. X sub I stands for initial position. Hopefully that helps. Okay, going on. Next concept. So we have a similar comparison in this section of our discussion. We have two words that kind of measure how fast something is going in real life. We have speed and we have velocity. So from our first topic of discussion this morning, we told you that speed is a scalar quantity because the speeds on your speedometer in your car can't be negative, okay? And the reason for that is because speed measures the distance an object travels divided by the time of travel. Distance could not be negative, if you remember from the previous page. So if distance can't be negative, therefore speed also can't be negative, okay? Velocity, however, can be negative because velocity is defined as the displacement an object travels divided by time. And remember, displacement can be negative, therefore velocity can also be negative. Okay, so this is a very popular test question for like an essay. What's the difference between speed and velocity? And we just kind of told you about that. So the main point is, remember, velocity can be negative depending on the direction that you're traveling. Okay. Also, just want to point this out. Speed is measured, speed and velocity measure distances traveled divided by time. That's where we get the units we see on speedometers. So we get like miles per hour because we have a unit of distance on the top and we have a unit of time on the bottom. So if you're ever dealing with distances over time units, whether it be miles per hour, whether it be meters per second, whether it be centimeters per millisecond, that's a velocity, okay? All right, going on. Okay, so on the note of velocity, we're going to introduce some equations to you in a moment that differentiate between something called average velocity and something called instantaneous velocity. Okay, and I've written an equation for you right here. I probably should have used the variables. I'll do that right now. The way I've written this says average velocity is equal to final position minus initial position divided by time. Okay, so average velocity is represented by a variable v with a line over it. Okay, remember that, it's going to be important coming up. So average velocity is equal to my final position, which we call x sub f, minus my initial position, x sub I, divided by the time that has elapsed. Okay, so that's your equation for average velocity. Okay, so let's illustrate this with another kind of silly example. So suppose that I'm at point A, let's call this like my house. Okay, and suppose that I'm going to go to point B, which is like my local donut shop, let's say. And suppose that that is a distance of 2 miles. Okay, and let's suppose that it took me 10 minutes to get there. Okay, so in this case, we'd call position A 0. Position B is 2 miles away. You can almost think of this like a number line if you want to. Okay, so you could do that if you wanted to, but just realize we're going a distance of 2 miles in 10 minutes. So my x sub f, my final position, would be 2. My initial position would be 0. And my time would be 10 minutes. So my average velocity would be equal to 2 minus 0 over 10, which equals 2 tenths, which can be reduced to 1/5, which is the same thing as 0.2 if you were to make this into a decimal. Okay, and that would be 0.2 miles over 1 minute. Okay, so that's an example of how you calculate average velocity using this equation. Now, instantaneous velocity is how fast an object is traveling at that particular instant in time. Okay, so measuring instantaneous velocity isn't very practical because unless we have like a radar gun, like the police have to track how fast something's going, or unless we have a speedometer in front of us, it's really difficult to know exactly how fast we're traveling at any point in time. Okay, so if you're driving in a car and you just happen to look at the speedometer and notice you're going 65 miles per hour on the freeway, at that exact instant in time, that is your instantaneous velocity. Whereas if you wanted to measure average velocity, you'd have to plug in your initial position and your final position and your time into the equation. Okay, next. All right, so introduce a new term to you. So remember, we've talked so far about displacement. We've talked about velocity. Now we're going to talk about acceleration. So remember, displacement could be negative, therefore velocity could be negative. Okay. Acceleration can also be negative, and we're going to tell you why in just a second. Okay, so just a summary of these three quantities we're kind of talking about today. Displacement is usually represented by the variable x, measured in meters. Velocity is usually represented by the variable v, measured in meters per second. Once again, we have that time per, that distance per time unit. Here's your equation for average velocity in case you didn't catch it on the last page. Now let's talk about acceleration. Okay, so when we talk about like acceleration is a measure of how quickly your velocity is changing per unit time. Okay, so if you've ever seen car commercials on TV, sometimes car companies will brag about their car's acceleration. So they'll say something like, this model can go from 0 to 60 in 3 seconds, or something like that. So that's measuring how quickly that car can speed up in a certain amount of time. Okay, the equation for average acceleration is listed here. It's kind of the same theme we saw before. So whenever you see a little f and a little I, that means final and initial. So here we have acceleration is equal to the final velocity minus the initial velocity divided by the time that has elapsed. Okay, you can feel free to write that on your notes in actual words, or if you're comfortable with the symbolic form of the equation, you can do that. Just remember A stands for acceleration. Now, something that's kind of weird is the unit we usually measure acceleration in. Acceleration is usually measured in meters per second squared. Okay, so I always had a hard time wrapping my head around that unit because it doesn't really seem to mean much. You know, at least with miles per hour, it kind of makes sense that velocity measures how many miles you're traveling in an hour. But when you're trying to understand what acceleration means when you're just looking at its unit, it's kind of weird. So what I would just suggest memorizing this unit and being able to recognize that whenever you see meters per second squared, that's an acceleration that you're looking at. Okay. All right, let's keep going. Okay, now this week you're going to be doing some assignments for me. The first few are pretty conceptual, just kind of asking you about the difference between vectors and scalars, asking about how to calculate displacements, velocities, accelerations. But the real meat of this topic is found in section 5, 6, and 7 of the topic for this week. Because in sections 5, 6, and 7, you're going to be using equations to do math with displacements, velocities, and accelerations. Okay, so I've got the equations you're going to be using in those sections listed right here. Okay, so you're going to want to write these down in your notes someplace. For quizzes and tests, I will allow you to use an equation sheet. So don't feel like you need to memorize these, but just be able to use them. So this can be overwhelming for a lot of physics students, and I remember when I first learned this, it was kind of overwhelming for me too, because we've got 5 equations here, and we already taught you 2 or 3 equations already up to this point in this lesson. Okay, so there's potentially like 7 or 8 equations you might need to know for this week to do the assignments. That's pretty overwhelming because how do you choose which equation to use? So here's my rule of thumb. Whenever you're solving problems using these equations, define each variable that's given to you in the problem, define the variable that they're asking for, and then pick the equation that's the best fit. Okay? We're gonna do an example right now. So I pasted one of your problems from the course into this document. We're gonna do it together. So this problem reads, at the end of a race, a runner decelerates from a velocity of 9 meters per second at a rate of 2 meters per second squared. How far does she travel in the next 5 seconds? What is her final velocity? Evaluate the result. Does it make sense? Okay, so first of all, they tell me that the runner decelerates from a velocity of 9 meters per second. So they started traveling 9 meters per second. So that's my initial velocity. Okay. They decelerated at a rate of 2 meters per second squared. Now remember, we just told you that whenever you see meters per second squared, that's an acceleration. Okay. How far does she travel in the next 5 seconds? Well, seconds measures time. Okay. What is her final velocity? So they're asking me for, hey, what is v sub f? What's her final velocity? Okay, so right here now, we've defined 4 variables that we're interested in this problem. So when I look down at my equation, I'm looking for an equation that incorporates these 4 variables. Okay, and you can see that it's not going to be this one because we didn't talk about displacements at all. It's not really going to be this one because we don't care about the average velocity. This one's looking pretty promising because it incorporates velocity, it incorporates initial velocity, acceleration, and time. Okay, this one's out because we didn't talk about displacement or position at all. And this one's out for the same reason. Okay, so take that approach whenever you're solving these problems. It'll save you a lot of stress when you can just check off equations that don't work and zero in on the one that does work. Okay, so my equation says that V is equal to V naught plus AT. Okay, just keep in mind V naught is the same thing as VI. Same thing, just for some reason, some textbooks just label it differently. So V naught's your initial velocity. Okay, so my velocity should be equal to my initial velocity. Okay, well, my initial velocity was 9 meters per second. I'm going to add on to that my acceleration, which was 2 meters per second squared. Oops, I got an extra line there. 2 meters per second squared multiplied by the time, which was 5.00. All right. Okay, so we've got ourselves an equation here. Now, we're going to follow order of operations. So multiplication comes first. So 2.00 times 5.00 is going to give us 10.0. Okay, remember we're using significant figures here. So if you forgot how to count sig figs and how to know how many sig figs should be in our answer, go back to topic 1 and review that. Then we're going to do our addition step. So we've got 9.00 plus 10.0. That's going to give me 19.0 meters per second. Okay, so that is the answer to part A. Okay, so in this example, the runner was running at a velocity of 9 meters per second at 2 and was decelerating at 2 meters per second squared. How far does she travel in the next 5 seconds? Now, there's a problem here, and I'm glad I made this mistake because this is a very important thing to note. When you're evaluating your answers to see if they make sense, this runner should be decelerating, okay, from a velocity of 9 meters per second. So I didn't catch that at the very beginning. Decelerating means to slow down, right? So what I should have done is make my acceleration negative, excuse me, because this person is slowing down. Okay, now that's going to impact our results. So let's change our answers since we kind of stumbled upon that realization. Remember, it's great to make mistakes in physics because it helps you clarify things. Okay, so when we do this, negative 2 times 5 gives us negative 10.0. Oops, that shouldn't be there. Negative 10.0, we're going to add that to 9.00. 9.00 plus minus 10.0 gives me negative 1.0. Okay, and that is the correct answer. All right. So remember, we had to go back and change our work because the object was decelerating, meaning it had a negative acceleration. Okay. Let's move on to part B. What is her final velocity? Oh, sorry. We already did point B. We just figured out her final velocity. What we should have done in part A, how far does she travel? So I'm a little out of order here. Sorry about that. Getting ahead of myself. We just did part B. We should have done part A. Okay, well, I'll just do things out of order. So let's go back to part A. How far does she travel in the next 5 seconds? Okay, so I'm going to reset my equation board so we can zero in on the equation we need. So they're asking how far does she travel? So they're asking us for a displacement. So they want x in this case. All right. So if we look at our equations, we don't really care about average velocity. We don't really care about average velocity, so that one's out as well. We just use this one for part B. Okay. We have 2 left. We have the fourth one listed here, which takes into account final position and initial position. And our last one kind of looks similar. It just doesn't have a time variable associated with it. Okay. So I'm going to say, let's go ahead and do this one, because it's got all the variables we have, and it's got the variable we want. Okay. Now, you might be asking yourself, well, how are we going to figure out what x and x naught are? I mean, x is our final position, which is what they're looking for. But how do I know what my initial position was? They didn't give me any numbers. So let's assume that our x naught in this case is 0. Let's assume that this runner is starting at 0.0. Okay. So if I want to figure out what my final position is, my initial position is 0. I'm going to add on to that my initial velocity, which is 9.00. Okay. We're going to add times that by the time which is elapsed, which we just figured out in, which we read from the problem was 5 seconds. And then we're going to add on to that 1/2 at squared. Well, our acceleration we said was -2, remember, because we're slowing down. Now we got that mistake this time. Glad we didn't do that again. And times by t squared, which was 5.00 squared. Running out of room. Hopefully I can fit it in here. Okay. Okay, now we're gonna probably need to get a calculator out at this point. So let me bring up my calculator. Calculator. Okay, it's taking its time. Okay, so let's go to our calculator. And if you have a handheld calculator on hand, that's always going to be the ideal case. But your Windows calculator is actually pretty useful. So we'll go to the scientific version. And that's going to load up for a second. So while that's loading, let's go ahead and start doing what we can on the problem. Okay, so we know that 9 times 5 in this first part of that equation, 9 times 5 is 45. Okay, then we have 1/2 times at squared. Okay, well 1/2 times -2 is -1. All right, and then 5 squared is 25. Okay, so we have 45.0 plus -1.00 times 25.0. So let's do our PEMDAS. -1 times 25 is -25. And then we have 45 plus -25. Yeah, it looks like we didn't really need a calculator for this one, actually. So this is a pretty nice problem. So 45 plus -25 gives me 20 meters. And that's how far the runner traveled. This is their final velocity at the end of the problem. Okay, now the last part of the question says evaluate the result. Does it make sense? So let's look at the distance traveled in part A. Does it make sense that a runner who was originally traveling at 9 meters per second and was decelerating in a period of 5 seconds traveled 20 meters? Yeah, that's pretty reasonable. 20 meters isn't that long of a distance for a runner to slow down and stop in. Let's look at our velocity. Does it make sense that a runner traveling at 9 meters per second, decelerating in over a period of 5 seconds, would then be traveling at -1 meters per second? Now that causes me to scratch my head a little bit because, remember, velocities can be negative, that's true. But if a velocity is negative, that means the person would be going backwards. So it doesn't really make sense for a person to be running forwards and slow down and stop and suddenly be running backwards. So just be aware that sometimes you need to kind of evaluate the real world practicality of the calculations you're doing. So half of our answer makes sense, half of our answer doesn't really make sense. Okay. But that's our answer. So you'd write an explanation saying, okay, well, yeah, it does make sense that they're traveling 20 meters. That's pretty reasonable. But our final answer says they're going -1.0 meters per second. That doesn't really make sense. Okay. So that's kind of what I want you to do in these kinds of problems. Now, I put another example down here. For the sake of time, you can do this on your own if you'd like. We actually started to do this example in class when we're having technical difficulties. So Go ahead and try this one on your own. Bullet in a gun is accelerated from the firing chamber to the end of a barrel at an average rate of 6.20 times 10 to the 5th meters per second squared. Okay, right then and there, little typo here. This should be times 10 to the 5th. Okay. For 8.10 times 10 to the negative 4th seconds, let's make that an exponent as well. What is its muzzle velocity? That is its final velocity. Okay, so it's up to you. You need to go through the list of equations. You need to identify the one that's going to get you to where you need to go. Okay, next section is on free fall. Okay, so the equations we just told you about in the previous page are good for any motion that has a constant acceleration. Okay, turns out that falling objects also experience a constant acceleration. Okay, so on the Earth, if you were to drop an object from a skyscraper, let's say, that object would experience an acceleration due to the gravitational force on that object. That gravitational acceleration we call g, and that g is equal to negative 9.8 meters per second squared. What that means is for every second that goes by that an object is falling, its speed is increasing by 9.8 meters per second. Okay, so here's my point. When you're doing free fall questions, you'll know it's a free fall question if it's an object that's experiencing the force of gravity. All you got to do is use the same equations we just taught you, just replace A with G. And G is negative 9.8 meters per second squared, so just plug that in and then solve for what you don't know. Okay, so in this example, we have a basketball referee tosses the ball straight up for the starting tip-off. At what velocity must a basketball player leave the ground to rise 1.25 meters above the floor in an attempt to get the ball? Okay, so we've got a couple of things they're telling us here. We want the basketball player to rise 1.25 meters. So they're giving us a final position they want us to be in. So we'll call that x sub f. Okay. If we're starting on the floor, even though it's not stated here, let's assume our initial position is 0. So we're going to make our floor 0 because it's the height of 0. They're asking at what velocity must the player leave the ground? So they're asking us, hey, what's the initial velocity that the player must have to leave the ground? Okay, and then because this person, when they're jumping up in the air, the only acceleration that they're experiencing is the acceleration due to gravity. So we can say, okay, well, we can assume that G, or A, if you're using the equations down below, is equal to negative 9.8 meters per second squared. Now, one thing I forgot to mention when we were introducing G to you, the reason why it's negative here is because gravity pulls things downward. So in this problem, because gravity is pulling the player down, we're going to make that negative 9.8 meters per second squared. Okay, so let's look at our equations. So we've got this one right here, which takes into account final position, initial position, average velocity, and time. Well, they didn't really tell us time in this question, so we don't care about that. Next one, average velocity equals initial plus final velocity over 2. Well, we didn't really care about average velocity in this problem. Next, we have velocity is equal to initial velocity plus acceleration times time. We don't know the time, doesn't matter. Next one, we can cross that out because we don't have time either. So this one right here at the bottom kind of looks like our best bet. Okay. So this equation says velocity squared is equal to initial velocity squared plus 2 times the acceleration times x minus x naught. So that's kind of the one I'm leaning towards right now. So let's start plugging stuff in. I want to know my initial velocity. Okay. Now, this equation has final velocity. Now, they didn't tell us a final velocity in the problem, though. So we have to do a little bit more inference here. imagine that you're this basketball player trying to get the ball. The referee's just tossed up. When you jump, you're going to reach the height that the ball is at. And for that instant, when you jump and reach up for that ball, you stopped going up and you're about to start coming down again. So basically, imagine like this is a graph of your height. So here's you on the floor. Here's you jumping up to get the ball. Here's you hitting the floor as you come back down. The ball is right here. So at this point, when you're getting the ball, your velocity is 0 because you're no longer going upward anymore. Okay? And in that instant of time, you're not coming down anymore either. You're not coming down yet either. So for that instant of time, you stopped traveling and your velocity is 0. Okay? So be prepared to make inferences like that. That's what makes these problems so tricky. If you forget to make inferences like that, you're going to get stuck and you're not going to know which equation to use. Okay? So I know that my final velocity is 0. So I'm going to start plugging things in. So 0 squared is equal to, well, I don't know what my initial velocity is, so we'll leave that as V0, and we'll figure it out by algebra. I'm plussing 2 times my acceleration, which we said was negative 9.8, since that's the acceleration due to gravity. Okay. And we're going to times that by our final position, which we're going to say is 1.25. That's the height that the ball is at, minus our initial position. We're going to make our initial position 0, since that's where we started from. Okay. Now, using some algebra here, we need to get V0 isolated. So let's start moving all the stuff on the right side to the other side of the equal sign so we can get V0 by itself. Okay, so let me pull up the calculator. Okay, so you can see I've got my writing over my calculator, so we can see a little bit better. I'm going to take 2, I'm going to times it by 9.8. And because that's negative, let's times it by -1 as well. And for some reason, that's not accepting that negative symbol. Oh, there we go. There's my negative button. And then I'm going to times that by, in parentheses, 1.25 minus 0, which doesn't really change it. Okay. So let me get my pen out again. So now we know that 0 squared is equal to V0 squared plus negative 23.25. Okay, so using algebra, let's go ahead, use our addition property of equality. Let's plus this 23.25 over to the other side. Okay, so plus whatever you do to one side of math, you got to do the other. 23.25. Okay, I'm going to get my typing up because that's going to be a little bit faster. So 23.25 should now be equal to V0 squared. Okay. So to get what V0 is, to cancel out that square, we're going to square root both sides. Square root both sides. Okay. So if I take 23.25 and I square root that, I get 4.82. 4.82. Let's go 4 sig figs because that's how many previous sig figs we started with. Actually, now let's talk sig figs actually for a second, because at the beginning of the problem up here where we were timesing 2 by negative 9.8 by 1.25, our least precise measurement had only 2 sig figs in it. Okay, so our answer should probably only have 2 figs in it. So 4.82 would be my answer, and that's meters per second. So in other words, back in this context of the problem, what this is saying is that in order for this basketball player to get up to reach that ball that's 1.25 meters above the ground, their velocity with which they push up against the ground with should be 4.82 meters per second. Okay. All right, so that's how you do some of these free fall problems. Once again, the only difference between what we've been doing and what we did in the previous page is that acceleration, we're going to make g, which is negative 9.8 meters per second squared. Again, here's one you can do on your own if you want. Kangaroo can jump over an object 2.5 meters high, calculate its vertical speed when it leaves the ground. How long is it in the air? This is pretty much the exact same setup as the problem we just did. All right, last thing I want to talk to you about today, and then I'm done, I promise. The last section of the topic that you're going to be studying this week is on graphs. All right, so this right here is a picture showing three separate graphs for the same object. The top graph charts the object's position, so how far it's traveling along the vertical axis versus how many seconds have passed by on our x-axis. The second graph charts its velocity, okay, versus time. And the third graph shows acceleration versus time. Okay, so a couple broad things to point out before we get into the details. This object starts by going 8 meters out about, and then it starts going back towards 0 and even surpasses 0 down to like -5. So this object is kind of doing what we did at the beginning of the lesson today. It's an object that's going out a certain distance, and then it's coming back, and even going beyond where we started. Okay, you can see that following this motion. Okay, notice that the object's velocity, it started out going pretty fast, like 14 meters per second. As it started going towards the U-turn point in this figure up here, so right there, when the object made the U-turn, that's for that instant in time, it wasn't going anywhere, so its velocity crossed the 0 line. And then because the object is going backwards along this portion up here, that explains why the velocity became negative, because it's going backwards. Remember, velocity can be negative if an object is traveling backwards. Okay. And lastly, in the acceleration graph, we can see that the acceleration is a constant -10. Okay, so this object is decelerating, okay, at a rate of -10 meters per second squared, meaning that even though it started going at a velocity of about 14 meters per second, at that time, it was already slowing down. Okay, and it was slowing down so much that even when the U-turn happened, that acceleration, that negative acceleration kept taking effect and made the object start to go backwards. It's kind of like the problem we did with the runner, okay, except this doesn't have a story attached to it, so it's free to not make sense. Okay, so let's talk a little bit of details and then we're done for the day. All I want you to understand from this picture is that velocity graph measures the slope of the position graph. Okay, and similarly, the acceleration graph measures the slope of the velocity graph. Now, this is a tricky concept, so I want you to pay close attention here. If you were to figure out the slope of each of these graphs, it would tell you something. Now, figuring out the slope of the top graph here is going to be difficult because the top graph, its slope is always changing because this graph is starting to curve. But what I'm saying is, if you were to measure the slope at different segments, like here, for example, if we were to keep this line going, that slope is going to match what you see down here. It's going to be about 15. If you were to measure the slope at the top of the path right here, that's a horizontal line, which is a slope of 0. You can see that's why the velocity crosses 0 there. And this last point, where the velocity is going at a slope equivalent to this line segment, that's going to be a slope that's equivalent to about -15. Okay? So it's kind of cool. Velocity measures the slope of the position graph. Okay, now let's talk about the acceleration. So if you look at the acceleration, we said the acceleration measures the slope of the velocity graph. Well, if you take a look at the slope of the velocity graph is a straight line right here, okay? So if you were to calculate that slope, and you can do that using techniques you learned in Algebra 1, remember the equation that says that slope is equal to y2 minus y1 over x2 minus x1? Remember that equation? If you did that using points on this graph, you'd probably figure out that the slope is negative 10. And because that line up in the velocity graph isn't curving, it's just a straight line, that's why the acceleration doesn't change. It's because the slope is the same all the time. All right? It's a pretty deep concept what we just talked to you about. But go over in your mind a few times. And if you have questions, please let me know, because there's lots of other examples we can give you. But start studying how these graphs relate to each other. Because when you can do that, you can analyze all sorts of aspects of motion. It opens a lot of doors. Okay, I promised we'd be done, and we are. So watch this video. If you've watched it and taken good notes, study it. It's going to help you on your homework and on the quiz that's coming up. Remember that I'd like all work done for topic 2 due by next week at midnight on the day that we meet, okay? And you can look at the schedule for the Zoom session to know what day it is. I'll go in and set the due dates though, so that it'll pop up when you click into the assignment. But by midnight of our next Zoom session, I want topic 2's work done. Okay, guys, thanks so much for watching, and we will see you at our next Zoom session. Bye.